and get my screen share going. Okay, so I just want to start by just reviewing and recalling what we did sort of at the second half of last class period. Because if you recall, what we had done was we proved that strict invariant types exist in NTP2 theories 2 classes ago. And we had proven that forking is always witnessed by such types, or Morley sequences in such types. And so what was left was to sort of assemble the ingredients for the Kim's lemma for NTP2 theories. So at the beginning of last class period, we did NTP2 theories, we did the Kim's lemma for NTP2 theories and concluded that forking equals dividing over models. And then we pivoted to starting to talk about NSOP1 theories. So the official definition of NSOP1 was quite strange, if you recall. It was this funny condition on trees, which says that you have some collection of tuples indexed by a binary tree, and you have some formula such that paths are consistent along those tuples indexed by a path. But if you have 2 incomparable nodes, one which extends the meet in the 0 direction, and the other one which is equal to the meet concatenated with 1, then they're inconsistent. So you have this condition here, which expresses when 2 nodes are inconsistent, and it's difficult to motivate and difficult to understand where that kind of configuration might come from, what its motivation is, why that would be useful. But there's an equivalent formulation, although the equivalence is not entirely obvious, which says that you can instead understand the property of SOP1 in terms of an array. And that's nice because trees are complicated and sequences are simple. So if you can sort of understand a tree property in terms of a sequence, that's often a helpful reduction in complexity. So what does it mean to be SOP1 in this array formulation? You have a collection of pairs of tuples, so Ci0, Ci1, which we're referring to as an array, and some natural number k, so that your formula phi xy will be consistent along the all zeros column. So this is like Ci0 as I varies. That's consistent. If you look at Ci1 as I varies, you get a collection of formulas that is k inconsistent. And then there's this funny condition that says that for every I, Ci0 and Ci1 have the same type over everything that is indexed by some j less than I. So everything that comes before. So we drew this picture here where the green indicates consistency, the red indicates k inconsistency, and the blue indicates that the elements at that level have the same type over the things that come below. And we sort of explained that if you look at the black lines that I've drawn here, that sort of indicates roughly where it comes from in the tree. You can think about the green as being a path, and you can think about the red as being the things that somehow go just off the path in the one direction, one step. And at least that has the right consistency inconsistency pattern. And the fact that that's equivalent turns out to be a consequence of this funny condition C that says that 2 things at the same level have the same type, because that tells you that by using many automorphisms, you can start copying the tree above, like the path above any given element to construct a tree. So that's not something we're going to do, although it looks very much like the proof that we gave earlier in this class, where we proved that long dividing chains are equivalent to trees of a certain height. Okay, so that idea was also just using a bunch of automorphisms, and a very similar idea will give you this proof. So, a very similar idea will give you this proof when k equals 2. When k is larger, you have to get it down to 2 inconsistency, and then you have to play some games. But it's nothing more complicated than making everything very indiscernible and playing games with formulas. It's the same kind of thing we've done before. So I think the more interesting thing is to relate this to some notion of forking, some notion of independence. And that's where the notion of Kim independence comes into play. So like I said, we were only going to concern ourselves with talking about Kim independence over models, because Kim independence is defined to be forking at a generic scale, or dividing at a generic scale. And no matter which theory we're working in, we have some notion of genericity, which comes from looking at Morley sequences in global finitely satisfiable types or global invariant types. And what's very special about models is that every type over a model has a global invariant extension, or a global finitely satisfiable extension even. And that's just not true over sets. If you have a type over a set, it need not be finitely satisfiable inside the set. So this is a fundamental difference between types over sets and types over models. And because we know that types over models always have generic sequences in them, according to some notion of genericity, we can sort of look at that case and then look at the dividing that happens at that scale. So that's the philosophy. Of course, then you might think, well, that's unsatisfying. Why do we have to restrict ourselves to models? And whether or not the theory will extend to arbitrary sets in any NSOP1 theory is a question which we don't know yet, and which is a topic of current research. So this restriction is unsatisfying, and we are trying to fix it. But at least at a first approximation, it's a nice place to start. So all right, what does it mean for a formula to Kim divide over M? Well, you look at the type of the parameter, and you take a global M invariant extension, and you look at a Morley sequence inside that type over M. So if for some such extension and some such Morley sequence, the formula divides with respect to that sequence, it Kim divides. So Kim dividing is just the dividing that is witnessed by Morley sequences in a global M invariant type. So what does it mean to divide? To divide says there's some indiscernible sequence such that your formula is inconsistent along the sequence. This is sort of restricting the indiscernible sequences that you look at. I'm not saying, I mean, maybe there are indiscernible sequences with respect to which my formula divides, but if none of those are Morley sequences in an M invariant type, then the formula does not Kim and divide. Okay, so this is just the dividing that happens with those sequences as the witnesses. All right, and then Kim forking is defined exactly as forking is. You Kim fork if you imply a finite disjunction of formulas that Kim divide, or equivalently, a definable set is a Kim forking definable set if it's contained in a finite union of Kim dividing sets. And then this gives you some independence notion, just like non-forking, where you say that the type of A over MB you say A is independent with B over M if the type of A over MB does not Kim divide over M, or Kim fork, over M. Cool, so this looks a lot like forking. It's exactly like forking and dividing, except that the notion of dividing is somehow weakened. So it's weaker to say, well, I guess the notion of dividing is strengthened, so the notion of independence is weakened. So I'm adding an additional condition for what it means to Kim divide. So if a formula divides, then it doesn't necessarily Kim divide, but if it Kim divides, then it necessarily divides. So Kim dividing is a stronger condition. I've added an additional condition. As a consequence, the notion of independence is weaker. The type of A over MB can divide without Kim dividing. All right, so the goal for today is to prove the following theorem, which characterizes NSOP1 in terms of a version of Kim's lemma. So Kim's lemma in simple theory says three things are equivalent. One of them is that the formula divides. The second is that the formula is inconsistent with respect to some Morley sequence. And then the third is that the formula is inconsistent along every Morley sequence. So those three things being equivalent characterizes simplicity theory. So we saw a different way of generalizing that result in SOP1, or sorry, in TP2, where we had to change the notion of genericity. So we said it's no longer perhaps the case that a formula divides if and only if it's inconsistent along every Morley sequence, but a formula divides if and only if it's inconsistent along every strict invariant Morley sequence. So by upgrading the notion of genericity, we were able to get the equivalence again. Now, it turns out that the equivalence of the second and the third, if your formula divides with respect to some Morley sequence, then it divides with respect to every Morley sequence, is true also in NSOP1 theories It's just no longer the case that dividing and Kim dividing are the same. So you somehow at the generic scale, you have for all exists if and only for all, but it's no longer characteristic of all dividing. So that's just a fundamental difference. But for that reason, you can think of this as a kind of Kim's lemma. It still changes the quantifier. So we have to decide which way to go first. So T is anisotropy 1 if and only if, whenever I take a model, if my formula Kim divides with respect to some M-invariant Morley sequence, then it divides with respect to all. So let's prove, I don't know, which direction should we do? It's hard to make these decisions. So I don't know, let's prove anisotropy 1 implies Kim's lemma first. So okay, so let's prove this direction first. Although really we will prove the contrapositive. So if Kim's lemma fails, then you find SOP1. So suppose Kim's lemma for Kim dividing fails. By the way, I mean, Byung-Han Kim absolutely hates that there are so many things named after him, or at least he'll say that he hates it. Maybe secretly he really likes it. But now there are these papers where you talk about Kim's lemma for Kim dividing, and then you have to talk about Kim-Pillay strong types and the Kim-Pillay criterion. And now Kim is himself writing these papers about Kim dividing, and you have Kim every place. And I don't know. I think it's actually very nice that there are things in math that are like named after people. It sort of reminds you of, I don't know. It's like building a statue, or something for someone. It's very pleasant, but it's also kind of fun that it gets on Byung-Han's nerves. I mean, it's very cute the extent to which it annoys him. So I don't know. I'm very tempted to keep naming things after Kim. Anyway, so we're now talking about Kim's lemma for Kim dividing failing. What does that mean? So there is some model of our theory and some formula phi xa that Kim divides over M, and a global M-invariant type, which I'll call R, extending the type of A over M such that for some equivalently all sequences I, which are, let's say, BI, no, let's call it AI. AI, I less than omega, Morley over M in R, phi x AI, I less than omega is consistent, right? So what does it mean to Kim divide? To Kim divide means that there's some global M-invariant type with respect to which you are inconsistent. And Kim's lemma says that if that happens with respect to some, then it happens with respect to all. So if that fails, then you Kim divide, but there's some other M-invariant Morley sequence with respect to which you're consistent. So you're inconsistent with respect to some, and you're consistent with respect to some. That's what it means for Kim's lemma to fail. So because phi x a Kim divides over A, or no, not A, M, sorry. There is a global M-invariant Q extending the type of A over M such that if I is, well, I should say what I is. or actually let's call it j because I already have an I. If j equals a prime I less than omega is Morley over m in q, then phi x a prime I less than omega is inconsistent. Okay, but it's an indiscernible sequence. If you have an indiscernible sequence and your firm is inconsistent along it, then it's k inconsistent for some k. Hence, k inconsistent for some k. Okay, so now we've got a q and an r. And now we're going to do something that looks totally bonkers. So does everyone remember like the tensor product on types? So we had some so let me briefly recall. So we had some like tensor product operation on types. So if you have like p and p prime, then p tensor p prime for global types is like the type of CD over the monster model, where D realizes P prime and C realizes P prime over the monster model together with D. And more generally, if you look at a type like P tensor to the linear order I, this is the type of, let's say, AI I in I over the monster model, where AI realizes P over the monster model and A less than I. So this is like the idea is the tensor product says first I realize P prime and then somehow over that realization. So in a free way, I realize P. So that's like two things are independent in some sense, and they both realize the types. Now the second thing, right, P tensor I is like the type of a Morley sequence in P indexed by I. So this is for I being in linear order. So for I a linear order. Okay, so this was some notion that we discussed a long time ago. We did this also in the context of finitely satisfiable types, and it turned out that these corresponded to the tensor product of ultrafilters when you took averages and so on and so forth. So this is a thing we did a while ago. Let's just recall it. So what is the bonkers thing we're going to do? We are going to look at the following type. So consider the following type. It's going to be R tensor Q tensor Z. Okay, that's a really crazy looking type, but let's realize it first. So let CI0, CI1, I in Z realize this type, R tensor Q tensor Z. Okay, so now let's just check out what we've got. So what does it mean to realize this thing? I mean, you've got a big bunch of tuples. So I guess we are going to index it this way. So let's say it's like this. And okay, this is like CI0, CI1. Okay. Now, one thing to notice is that if I just restrict attention to the things indexed by I comma 0, this sequence, this is a Morley sequence in what type? It's a Morley sequence in R. Here I've just realized R each time. So the left coordinate corresponds to a Morley sequence inside R. So this is a Morley sequence in R tensor Z. Oh, sorry, I should say where I'm realizing this. Let's realize it over M. Okay, so this is a Morley sequence in M. And what does that imply? That implies that phi x ci0 I in Z is consistent. Why? Well, R was taken to be the invariant type that witnesses that Kim's lemma for Kim dividing fails. So what that means is that we chose R so that the formula is consistent along Morley sequences in that type. So great. That means that this column is consistent. So let's mark that in green. Very good. So that is our first step. That column is consistent. Great. Now, if we look at the ones column, this, if you see here, we chose this to be a Morley sequence inside of Q. So Ci1, as I ranges over the integers, is a Morley sequence indexed by the integers in over M in Q. And that implies that phi x Ci1 I in Z is K inconsistent. Okay, why? Well, again, Q was chosen to be the M-invariant type that witnessed that the formula Kim divides. And we chose K to be the amount of inconsistency that you get there. So this is the type such that Morley sequences inside this type have the property that if you move the formula along that sequence, you get something K inconsistent. So that means that the formula, as I move it along the Ci1s, is also K inconsistent. Very good. So that means we can draw this column in red. Okay, and now we look very close to being a what am I trying to say? An SOP1 array, like we saw before. What we're missing is this condition about any two things having the same type. So how can we fix that? Well, here's where we use the fact that we have invariant types in an essential way, and the fact that these extend the common type. So we know that okay, if I fix an integer, so I look at I in the integers, and I look at Ci0, this realizes what? Well, in particular, it realizes R over the model, which is the same thing as the type of A over M, because R extended the type of A over M, which is the same thing as Q restricted to M, because Q also extended the type of A over M. And we also know that Ci1 was chosen to be a realization of Q over M in particular. So this implies that Ci0 has the same type over M as Ci1. Okay, so this is just saying that because both R and Q extend a common type over the model, any one of its realizations, if I choose a realization of Q and a realization of R, they will still have the same type of the model, because whatever type they realize, its restriction to the model is the same. Okay, that's very good. And then we know that if I look at C bar greater than I, that's like all of this stuff. This stuff realizes a global M-invariant type indexed by what? It's indexed, I mean, this is a Morley sequence indexed by the natural numbers. So this is like indexed by the natural numbers because it starts here. So this sequence will realize R tensor Q tensor omega over some stuff, but in particular, it will realize it over C bar I. So think about it this way. I have the sequence of pairs, and I know that at each stage, I realize my type over everything that's below it. So this sequence of pairs is a Morley sequence in the type R tensor Q over all the stuff before. So in particular, it realizes that over M C bar I. And since Ci0 has the same type over M as Ci1, and R tensor Q is M invariant, any relation that a realization of R tensor Q tensor omega has with Ci0, it must also have with Ci1 because they have the same type over M. So this implies that Ci0 has the same type over M as C bar greater than I as Ci1. And this explains ultimately why we indexed everything by the integers, because now what we've got is exactly the condition that we need to be an SOP1 array, but upside down. So defining C prime I 0, C prime I1 as equal to, let's say, C minus I 0, C minus I 1 for all I less than omega, we have three conditions. One will say that phi x C prime I 0, I less than omega. That's not what that's supposed to look like. I less than omega is consistent. Two, we'll say phi x C prime I 1, I less than omega is k inconsistent. And because we switched from positive to negative, now we changed the direction of the order. So what we've said now is that C prime I0 has the same type over M as C bar prime less than I C prime I1. Okay, so that implies by our array configuration that phi has SOP1, and that concludes this direction. Okay, very good. So this shows you that if you are if you're in SOP1, Kim's lemma must hold. So we've proved that Kim's lemma for Kim dividing holds in SOP1 theories. And now what we'd like to do is reverse the direction and to prove this, prove that it characterizes in SOP1 theories, which is nice. Okay, so now let's go the other direction. So what we will prove now is that SOP1 implies Kim's lemma fails. Great. Okay, so again, we're going to use this array. And what excites me about this class is that, okay, the proof is by average types. And I think that most of the time when I've given this proof, I've had to sort of explain what average types are and to develop the whole theory and explain what invariant types are. And what's fun is that like we did it, you know, like we started this class talking about average types along sequences because we used that to prove this theorem that whenever you have a sequence, you can find an indiscernible sequence that realizes its EM type. And so now we can just use these tools that we've developed and we'll get a very quick proof. So okay, we've assumed that we have SOP1, so we can go ahead and find our array. So there is an array, but actually before we do that, what we're going to do is we're going to try to produce a failure of Kim's lemma, not over an arbitrary set, but over a model. So we need some way of producing a model. And for that, we're going to add Skolem functions. So let me just recall very quickly what Skolem functions are, although I think everyone here probably knows. So we say T has Skolem functions. So this will just be a definition. If for every formula phi x y with, let's say x is a singleton, although y doesn't need to be, there is a function, like a definable function. Well, let's just say it's a function. F sub phi of y such that T will prove for every y, if there exists an x such that phi x y, sorry, that's looking very ugly. Let me fix that. If there's an x such that phi x y, then phi of f phi of y holds. Okay, so what does this say? This says that if your formula phi xy for a fixed parameter y defines a non-empty set, so there's some element in it. If there exists an x such that phi xy holds, then f of y will pick one of those elements. It'll pick an element out of that non-empty set. Now, if you have a theory, you can always expand it in some way to add Skolem functions. So for example, one way, which is probably the conceptually simplest way of doing it, is you just fix by the axiom of choice well ordering on the model. And then whenever you have a non-empty set, the least element is definable, provided that you've added that well ordering to the language. So what you do is you can just sort of add a new binary relation to the language for a linear order. You well order the model and you interpret this new symbol as the well ordering. And now every definable set has a definable least element. And so you have Skolem functions. There are reasons that sometimes maybe you want this to be done by terms. So then you would need to like add a function symbol for each one of these formulas. But okay, they're just different ways. But the main thing is that if you have Skolem functions, then whenever you take definable closure of a set, you get a model. So if T has Skolem functions, then for any set of parameters, let's say X or say A, DCLA is a model by, I forget what this is called. It's something like the Vought test or Tarski-Vought. Okay, so a substructure is an elementary substructure if whenever some formula of the of the form exists X Vx A is true in the superstructure where the parameters in the base structure, then that statement is true downstairs. So as long as you can put witnesses in for all of the definable sets, then you have to be an elementary substructure. So in particular, you have to be a model. So DCL is always the substructure. What is it, an elementary substructure? Well, it will be if you've added in witnesses to all these sets, and these functions have made sure that you will. So good. Okay, so what we will do, so now that ends my little digression on Skolem functions. Did you guys do this like in model theory? Did you talk about like Ehrenfeucht-Mostovsky models and things? Okay, so what we're going to do is basically produce an Ehrenfeucht-Mostovsky model of an array. So now assume T has SOP1 and let phi xy be a formula witnessing this. So expand T to TSK, a theory with Skolem functions. You can, like I said, there are various ways of doing this. Just pick one, anyone you like. Then we can find an array inside the monster model of TSK, CI0, CI1. Let's see. I think indexing it by omega is good enough, such that, okay, I'm going to say 4 things happen. So one of them is that phi x CI0, I less than omega, is consistent. 2 is that phi x CI1, I less than omega, is inconsistent. 3 is that CI0 has the same type as everything that comes below as CI1. And then the 4th condition, which is the one that we're going to sort of add, is, oh, and let me say this is with respect to the language LSK. And the 4th condition is just going to say that the sequence of pairs of tuples is indiscernible with respect to the Skolemized language. Okay, so why can we find this? So the first question you might ask is, okay, how do I know that the sequence of pairs can be made indiscernible? And that is something which we've done millions of times in this class. If you have some sequence, you can just extract an indiscernible sequence using the theorems that we proved at the beginning of class. So just replace it with an indiscernible sequence that realizes the same EM type, and notice that the various conditions that you need, like the inconsistency of the ones column, the consistency of the zeros column, these are preserved because they're encoded in the EM type. Okay, so that you can do. But a more subtle point is, how do you know that CI0 can be taken to have the same type as CI1 over everything that comes below with respect to LSK rather than L, right? The array's condition that the definition of the array gives you is just that CI0 has the same type as CI1 with respect to the language L as C bar less than I. If you add new structure, there's no reason to believe that those two things have the same type with respect to the larger language. So actually, it might not be true. Of course, like maybe you have some Skolem function which picks CI0 as a witness, and it doesn't pick CI1, and then it differentiates these two elements. All right, so to get this, you sort of have to go into the proof of the equivalence. Of course, if you think about the tree definition of SOP1 will show you that this formula will witness SOP1 with respect to the same tree, regardless of any way of expanding the structure. So you could throw in all kinds of new predicate symbols and new functions, whatever, but the old formula and the old tree, with respect to the original language, will still witness SOP1. That's a piece of cake. Then you sort of run the same argument to find the array. Now, instead of with respect to the old language, with respect to the new language, with respect to this richer language. And so the fact that this equivalence holds whenever you have a formula with SOP1 tells you that, okay, the condition in condition 3 can be taken with respect to this larger language. So this is a somewhat subtle point, but we'll need this, so it's worth bearing in mind. All right, so we can arrange all of these things, these 4 conditions. So what we will do now is something that's kind of fun. We're just going to cook up the correct average types and observe that they do what we want. So what we will do now is we will let M be the DCL in the Skolemized language of the whole sequence of pairs. So that's a model. So it's a model in the big language, but of course its reduct to L will be a model of T. So if I think of M, so actually let's call this MSK. And then what we can say is that, okay, if I look at MSK and I take its reduct to L, let's call that M, which is a model of T. Because LSK, I mean, TSK is a Skolem, it's an expansion of T. So if I take any reduct of a model of TSK to the original language, I get a model of T. Very good. So now what we will do is we will let D be a non-principal ultrafilter on M concentrating on the all zeros column, Ci 0, I less than omega. Okay. So we choose an ultrafilter that says the zeros column, the zeros column is big. So how do you do that? Well, you just notice that that set by itself is a filter. It's certainly a family of sets that contains just one set is it's closed under union, and then you can take its upwards closure, and then that will so it generates a filter, right? Then extend that to an ultrafilter in any way you like. Then that's going to be D. Likewise, we will let E be a non-principal ultrafilter on M concentrating on the ones column. Okay. And what we'll do is we will consider two types. So one of them will be a type which we will call R, which is going to be the average type of D over the monster model, and one type which is Q, which is the average type of E over the monster model. Okay, so the first thing to observe is if I look at, so let me call this a claim 1. If I look at a Morley sequence, which we'll call AI I less than omega, is Morley in let's say Morley in R over M, then phi x Ci 0 I less than omega is consistent. Oh, sorry, I should have said A. Okay, so if I take a Morley sequence instead of R, that's consistent. Why? Well, because R is equal to this average type, and phi x Ci 0 I less than omega is consistent. Right? So let me sort of draw a picture here, because I think it's worth seeing what's happening. Okay, so here we've got M, and we've got these two columns. So one of them is the zeros column, and the other one is this ones column, which I'm going to label red. And we've got these two ultrafilters. One is concentrating on the green column. So that's like here. And then we've got one which is concentrating on the red column, which is E. And the idea is Okay, first I'm going to realize a Morley sequence inside of the green column, which we're going to call I. Now, why is that consistent? Well, let's just think about it for a second. If I take a point here, okay, is it consistent with the green column? Well, it's going to be consistent with any point. If I pick a point in the green column, the type of the blue element at the top says I'm consistent with this blue thing at the bottom, if and only if that point to the the blue point at the bottom is consistent with a large set of points in the green column according to the ultrafilter D. But that blue point in the bottom is consistent with everything in the green column. So of course, it's going to be consistent with the blue point at the top. Now I ask about the second blue point. Is this blue point consistent with the first blue point? Well, it's going to be consistent with the first blue point, because that first blue point is consistent with everything inside the green column. And that means that the type that says I'm consistent with a particular element of the green column goes in the type. I mean, the formula which says that goes in the type. So it's very easy just using the definition of average type to see that that this green sequence that I built here, this I, gives you something which is consistent. Just unraveling the definition of average type. Then we're going to look at a Morley sequence inside of the red column. This is like claim 2. So if J is equal to Bi, I less than omega, is Morley over M in, I believe this one was called Q. So this type here gives you is something we called R. This type here is something we called Q. Then phi x ci1 I less than omega is K inconsistent. Well, okay. Okay, this is K inconsistent, which implies that phi x bi I less than omega is K inconsistent. Okay, so so far so good. Then claim 3. And here's where we really use the fact that, well, okay, here's where we use the fact that any two elements at the same row have the same type over everything that comes below. So we claim that if we look at R restricted to M, that's the same as Q restricted to M. Why? Well, it suffices to show that if I look at the average type with respect to the language LSK of D over this sequence, C bar less than omega, that's the same as the average type of LSK with respect to E over C bar less than omega. Why? Well, because with respect to this larger language, with respect to this Skolmei's language, M is just the DCL of C bar less than omega. So if two things have the same type over a set, then they have the same type over the DCL of that set. That's easy to show. Because of course, if you have definable functions that give you new parameters, then you could translate any formula that uses parameters from the DCL to a different formula that uses parameters just coming from the set, by just putting the definable functions into the formula. So it's enough to show these two things. And so, okay, let's just do it. So suppose you take some formula, let's say phi x, which, I don't know, has parameters from C bar less than n, which is in the average type of L. Oh, let me use a different formula. Let's call it C. Okay, so anytime I take a formula, which is in this type, that happens if and only if the set of I, or sorry, the set of Ci0 such that I is bigger than n and Ci0 C bar less than n is true is in D. And then by indiscernibility, that happens if and only if the collection of Ci0 such that I is bigger than n contains the set of Ci0 such that this formula is true. Okay, why? Well, look, if your formula, because of indiscernibility, if this formula is satisfied by some Ci0 for I bigger than n, then it has to be satisfied by every Ci0 for I bigger than n. Because of indiscernibility, right? If it's true for one, then it has to be true for all because they all sit in the same order relation with respect to the numbers less than n. So the only way for this first set here to be inside the ultrafilter is if it, if it's in the ultrafilter at all, then it has to be non-empty. And if it's non-empty, then by indiscernibility, it has to be everything bigger than n. Does that make sense? This is just what indiscernibility gives you. But okay, then we use the fact that in the anisotropy 1 array, two things at the same level have the same type over everything that comes before. So this happens if and only if Ci1 such that I is bigger than n contains the set of Ci. Oh wait, let me. Sorry, I have my containment the opposite direction. Of course, it's possible that there are things of lower index that live there. Sorry. So this is contained in set of Ci1 such that this formula is true. C bar less than n. Okay, I just copied the thing from above. And then that happens if and only if C x C bar less than n is in the average type with respect to LSK of E over C bar less than omega. So that does it. These two types are the same. So what did we do? We found two global M-invariant types, both extending the same type over the monster model, or sorry, over the model M, one of which gives me something inconsistent, the other of which gives me something consistent. So if A realizes, let's say, R over M, which is the same thing as Q over M, then phi xa Kim divides over M witnessed by Q, and Kim's lemma fails witnessed by R. Okay, and that concludes the proof of the theorem. So that's it for what I wanted to say today. We'll sort of briefly go over this next time, then we'll start in on a proof of symmetry of Kim independence, which will be the last thing we do about anisotropy 1 theories, and it'll probably take 2 days. So that's the plan. Are there any questions about what happened today? No? Okay, cool. So I will see you all bright and early on Wednesday when we will continue with anisotropy 1.